All right, thanks, Carlos, for the introduction. So thanks for coming to this session. So I'm going to talk about numerical phantoms for validating diffusion MRI techniques. So I have one conflict of interest to declare, which is I occasionally speak for the Philips Healthcare. So I think when I was asked to do this little talk, and I had asked myself the question, so what is a numerical phantom? Sounds like a really obvious question, but actually when I Googled it, I couldn't find an answer. I don't know anybody of you tried. So, and I think perhaps you saw the picture I showed previously, you probably thought actually maybe what you see is what you get. I know it when I see it, so obviously, this is not a stupid thing to say when the Supreme Court judge just to say the same thing. So, and we can clearly see which one are numerical phantoms, which one is not. But being a scientist, I'd like to see a bit more and say maybe give it some definition. So I find inspiration from things I do know. So Shep Logan phantom is a very well-known phantom in imaging, especially in CT, for example. So how do they define that? And that's what from Wikipedia, which says the Shep-Logan phantom is a standard test image created by Larry Shep and Benjamin Logan. So I think the key word, the standard test image, would that be a very good definition for the phantom we're interested in? So if you look for standard test image, it has an entry and has an example, which turns out to be the LENA. For people who do image processing, you must have seen that before. And I think I would argue that's probably not what I would argue constitute the kind of numerical phantom that we're interested in. So I think we should read on to that definition of the phantom from Shep Logan a bit more. So the key word, I think, is the word model. It serves as a model of a human head in the development and testing of image reconstruction. I think that the key word model is important. And I think in the contrast to that, the LENA is an example where in many ways it's not a model because it lacks the controllability, flexibility of changing the components within that image. And so the Shep-Logan, in contrast, a lot of flexibility, as I will illustrate a bit more in a couple of slides later. So with that in mind, and I think I come up with this, just a working definition, perhaps for this talk. I think of numerical phantom as a computer model that we construct to represent some physical object or phenomena, and that allows to enable computerized testing and verification. So that's my working definition I will hope to follow for this talk. And so what makes a good one? I think that's the next question. To meet these criteria as defined at the bottom. And so we go backward, and I think, of course, it should be designed in such a way with a well-defined verification purpose or perhaps purposes in mind. So that's important. So we know what we wanted to use it for. And to fulfill that purpose, we need to represent the relevant object, the physical object or phenomena, sufficiently well for the stated verification purposes. So I think I emphasize we're not here to build a perfect model that perfectly manifests the real world. That's not the goal here. We know that's probably an aspiration we can go for, but I think in practice, if we can get something that is capture the essence we're interested in monitor, that will be a good thing. That will be useful. And we'd like them to be flexible, controllable. That's really the unique selling point in my mind for numerical phantoms, in contrast to other type of phantoms that we'll hear about later today. So that's an example using the Shep-Logan phantom. So you can see that it is prescribed by a set of well-defined operations, parameters or objects in that picture, such as a set of ellipses, where the center of the ellipses are, what are the major axes, what are the minor axes, and the orientation of these axes, and the color intensity scale. All these are precisely prescribed, and you can change them to the way you want. So that allows it to be very flexible and highly controllable. And of course, being numerical phantom, they are computer tools essentially, or recipes. They should be easy to use, and I think Shep-Logan is relatively easy to use. And I think it's important for any computational tools, they are open source. So they're open for scrutiny and make it much more reproducible. And I think these are some of the things when I think about a numerical phantom, which makes a good one. So when do we need them in a context of diffusion MRI? I think we heard a lot from Jeff and from Evan earlier And I think I'm going to focus on, one of the key area where I think numerical phantom really play a huge role, which is the model-based microstructure imaging, something I work a lot on. And here's an illustration of the process, which is, I think everyone already explained, where the goal is to take the signal, which are these images, which we measure, and somehow try to estimate the bottom, which is the histology, which captures things like cell size, shape, density, orientation distribution, as well as such as membrane permeability. These are the things that are really interesting we want to measure, and we want to measure them from signal. And in a model-based approach, trying to do that by produce a model that captures these tissue properties and use them to predict the signal you might see and compare them as a way of trying to find the right parameter. So that's what the one aspect to focus on. I will touch on also on the mapping structure connectivity, and I think it's a very, very topical area. But on the other hand, I think many other forms of phantom are much more well suited for that. But I'll give a few examples on that. Okay. So let me start with looking at the model-based microstructure imaging, how we can use numerical phantoms to tackle these problems. And going back to this figure again, so this is what the object of interest. So what should the phantom design to do? And I think, in my view, what we need is design a computerized tissue in place of the physical tissue, which we can prescribe precise properties of cell size, shape, density, or permeability if you're interested in that, as well as orientation distribution, and use that using a very accurate, or as accurate as possible, mathematical formulation to simulate the signal, such as the tools that everyone talk about, to produce a signal. Then we can actually use the model-based tools you developed and trying to estimate from the signal the same parameter you prescribed. And that allows you to directly verify those parameters. I think that's really a very useful way of looking at these type of applications. So, and there are many ways to do that, as everyone mentioned. So I think the one which is perhaps most popular is known as the Monte Carlo diffusion simulation. So you start by prescribing, as I say, a computerized tissue, which is, in a simple sense, a set of geometries, usually prescribing boundaries. These boundaries can be permeable, means water molecules are allowed to go through, or not. In this case, I'm having a set of cylinders, they're impermeable. And then you let them undergo a computer simulation of random walk. That's why the word, hence the word Monte Carlo. And I'm not going to go into detail of that, just going to show you quickly what it looks like. So essentially, you throw in a bunch of virtual particles that undergoing a random walk, which is programmed, and then they traversing space every time the trajectory going across this membrane boundary, which again, virtual, and you can detect them, then you make decisions about what to do. They should be reflected, or they should be going through occasionally, et cetera, et cetera. So that allows you to look to essentially follow these particles, their position over time, over more than one particle, thousands or millions of particles as you wish. But that's not what we measure in diffusion. What we measure in diffusion is not the position, but the relative position, the position of each particle relative to their starting point, or displacement. So you derive from the simulation the displacement distribution, and that allows you to prescribe a set of diffusion sequence, as everyone explained, that creates the simulated signal that we're interested in. And that's a signal you can use to estimate using your model-based tools to predict, for example, the size or density of the axons, and you compare with your computerized tissue and see whether they actually match. So that's how it works. And so there are a few key challenges in doing so. I think I'll just give you an idea. First, we want to make sure the substrates are flexible and controllable, and they should be useful to reflect the truth. So for example, the starting points usually are these parallel cylinders, impermeable or permeable. They're usually of the same size, pointing in the same directions. And then we start to looking at crossing fibers, such as you can have different pools which go in different ways. And you can also have curving fibers, which is modeling such as undulation. Or you can have a beading, where to model some of the pathological processes. Or if you really go crazy, you can have these type of spaghetti balls, which is, I think, potentially a way to capture, say, gray matter, perhaps. So these become increasingly more complex to do, and it requires a lot of development effort. So the other aspect is the actual simulation of the dynamics, such as we want to make sure the random walk, little walker, little virtual molecule, virtual water particles, they are dancing around in the prescribed environment in a realistic way. And so this is what a picture from Bowles I saw in their MRM paper in 2009, which is still here. And so the little red ball representing your little particle, and the little triangle represent a particular surface the particle will take a random walk, will actually collide with. So there's a decision to be made. So the standard decision is reflected, either elastically, inelastically, or with relaxation. So if you want to model permeability, you should allow occasionally to let it go through, and then you can prescribe the probability for it to do so. So these are the behavior you want to be able to prescribe in your simulation, so to be having a very accurate random walk dynamics. So I think these are the two key challenges. And so in the next few minutes, I'm going to give you a set of examples to see how diffusion simulation allows you to look at real diffusion MRI challenges. So I will go back to 1995. I think there are many use of Monte Carlo simulation in the literature. I think in the context of diffusion MRI, that's probably the earliest I can go back to. So this is, even though it's one of the earliest in 1995, it's probably in many ways still not surpassed by the current type of simulator in practice. So as a text, the abstract on the right illustrate. So the goal here is trying to develop a theoretical model for water diffusion in tissues. And they do so by deriving that model, here, hence analytically, and then compare that numerically to here the Monte Carlo simulation. So Monte Carlo simulation here provides a tool, as we say, the validating the analytical model developed. And it's a fairly sophisticated model, although they're representing cells, a set of periodic boxes. But I think what's interesting is it allows these boxes to be permeable. Particle can go through them. And so they also allows for the wall relaxation, which I think make it really complex geometry situation. So the next example is almost more than 15 years later, which is kickstart some of the model-based approach that become of interest in the last 5-10 years. And so this is work by Dan Alexander. And so the Monte Carlo simulation here was used to construct a set of a mimic of the corpus callosum, of different parts of the corpus callosum, from the genu to mid-body to splenium, where biologists has analyzed these sections of the brain tissue and prescribe and determine the distribution of different, from small to large axons. You can clearly see the genu and mid-body and splenium are very, very different. And with Monte Carlo simulation, we can prescribe very flexibly these mimic of the underlying tissue, and then in turn can be applied to test whether the technique that's proposed here can estimate axon diameter reliably or not. And one particular important outcome of this particular work is it allows you to understand precisely the limit, as Jeff mentioned earlier on, the range of value where we can probe. And in this instance, despite we are at the current gradient strength for the clinical systems, we are limited in terms of measuring very, very small axons, such as this. But I think because of the distribution, we can still actually have sensitivity to, say, such distribution from a, say mid-body, where you have much larger axons, to splenium. So next example, looking at using Monte Carlo simulation for crossing fiber resolution. It's a very hot topic for many years. And so there are a lot of numerical phantoms in this area, which I'm not going to talk about. So this is probably, I would say, represent the state of the art, where the signal for each voxel are simulated using Monte Carlo simulation, which probably represent the closest we've got to the real signals. And here we can prescribe precisely the proportions of these different populations. We can prescribe precisely the angle of these crossing fibers. We can prescribe many other things, number of crossing fibers. And as a result, we can now start to ask questions in the validation, how accurate the fiber orientation estimated, and how much, whether we got the compartment fractions right, and whether we got the number of bundles correct. So this is really a very, I think, the best illustration of using simulators for looking at crossing fiber validation. So next example, looking at more cutting-edge work on looking at permeability. So in this case, there's a very well-known model called Karger model, as it says here, And so there, in 2010, two groups actually almost simultaneously published this apologies. So the work from Nielsen is actually, Marcus is in the JMR in 2010 as well. I forgot to include the journal here. But the goal here is trying to use Monte Carlo simulation where we can prescribe precisely the amount of permeability or the chances where a particle can go through or go back into a cylinder. And so in this case, they take a slightly different approach, but arrive at a very similar conclusion such that we know that Cargill model is only a good approximation when the permeability is very, very low. So basically when we go from a very impermeable wall to slightly permeable wall where the Cargill model can be used, but not much further. So next example, looking at the pathology. This is work by Matthew Budd, and he's going to speak, I'm sure, about it a bit later. And here the key question is to understand whether the neurite beating which is observed in tissue, whether it actually can constitute a factor that decreases the apparent diffusion and decrease in ischemic stroke. So this is a very good example where numerical phantom can be useful, where it's perhaps difficult to modulate these things in physical phantoms. Here we can at least test in a very simple case by manipulating the amount of beating in phantom to see whether we see the desired effect. If there's no effect from physical phantom, chances are this is likely not to be a major contributor in the real world. Okay. So the next example, looking at undulation, as I mentioned earlier, where in many parts of the neuronal tissue, the axons are not straight. So really going in an undulation fashion. And so what Nielsen Marcus did in 2012 is he created a computational model which is looking at mimic these undulation as illustrated here, and he proposed a mathematical model to determine these properties, as well as using simulation to validate that. And one of the key findings illustrated to the right here is that when there is a presence of microscopic undulation, that is, when the undulation frequency is sufficiently small, such that the water molecules in the time frame we're looking at it has time to traversing through them, then the effect becomes quite pronounced. And so what you see here, these solid curved, dark curved, are the undulating fibers, and if you actually compute them from simulation. And the dashed lines are a set of non-undulating, that is straight axons of different diameters. And you can see here, so the top one corresponds to a diameter of 2 micron, the next one is 6 micron, and the bottom one is 12 micron. And the undulation actual diameter is only 1 micron. So in essence, by ignoring the undulation, you're going to overestimate the amount of axon diameter, which I think is a very useful knowledge to gain from simulation. One more example here, looking at something very topical in the last few years, looking at the time dependence of the extracellular diffusion. And there's a series of papers published in the last year or two, looking at how that dependence is important for, say, axon diameter estimation, such as the top one, these two NeuroImage paper, and as well as looking at whether we can measure these time dependency using MRI, such as using frequency-dependent spectrum analysis. And so in all these cases, diffusion simulator played a key role in that. Okay. So the final example in this area, I'm going to look at the G ratio, which is, again, become quite prominent recently, which essentially measure the ratio of the inner diameter of the axons to the outer diameter, which is including the myelin. So the G ratio is known to supposed to have an optimal value around 0.7, and so any deviation from that, either too high or too low, become problematic. And so in this work, which is Nicholas Stikov in 2011, and so they used diffusion simulation to look at whether FA can be used as a predictor of the fiber volume fraction, which is one of the values you need to compute G ratio. And in this case, they realized that FA can be affected by orientation as well as packing density. So they only look at areas where orientation is known to be highly coherent, so corpus callosum, that is. And so in this case, you have very highly parallel cylinders. They use Monte Carlo simulation to identify the relationship between fractional anisotropy and a fiber count for a range of diameters. So these three curves are actually for different regions as well. And so they can produce this essential calibration of how you can read off from FA measured value to the fiber volume fraction. And as a result, you can now take FA value measured from DTI and then read off its FA fiber volume fraction. And together with another value which you can measure called bond pool fraction, you can produce a myelin G ratio. And this is the result they got, which is, I think, it's in the right range of value. And more recently, they extended this work in 2005, and I think so. But this is an example where a simulation can play a very important role. So, okay, hopefully that makes you excited about trying this. And I think the good news is there are a number of tools available. I think probably the most popular ones, so out of all the example I gave you, 60% of them use a Camino simulator, which is the method described in Hall et al. In 2009, and it's available as an open source toolkit, which is as part of the Camino. And then there's also more recently a diffusion microscopy simulator, which is published in +1 in 2013, but I'm not aware it's available as a public software to download. And the second tool that actually is publicly available is this DWMRI random walk simulator developed by Landman et al. And published in 2009. It's really excellent tools. And you can, again, download it from the Nitric website here. And the fourth one that I'm aware of is called DivSim, and developed by Balls or Greg Baxter now in 2013 now. So I struggled. I couldn't find a website, but I'm sure if you contact Greg, you probably get directed to a download link. And also, I didn't list it here, is the work which is earlier from the G ratio calculation. As I understand, there's a software available, but I couldn't find it. But you can contact Nicholas Stikov to get access to that. So there are a few alternatives. Monte Carlo diffusion is not the only way to do this analysis. As Everett mentioned, you can directly solve the diffusion equation or block-Tor equations. And so there are a number of ways to do that. So early on, in 2002 to 2003, and more recently, people have been using a technique called finite differences. It's basically a simple discretization of the partial differential equation involved. And there's a more powerful technique, perhaps numerically more robust. It's called the finite element method, also become quite popular. And in this situation, the challenge is to actually represent your substrates in these nice, fine meshes, which represents a genuine computational challenge. But I think it really provides a very useful way to not just alternative, but also perhaps to compare and validate your Monte Carlo simulation itself. So everything you develop mathematically, programmatically need to be validating somehow. So having two alternative techniques allows you to kind of check against one another. Okay, so in the next few minutes, I'm going to look at quickly the tractography and structure connectivity, how numerical phantom look at that. So this is a really good example, which is this ball of spaghetti phantom called numerical fiber generator. And it's a really flexible tool and has a lot of flexibility. What I think is really nice is illustrating this paper. It allows you to construct a connectivity matrix where you know the ground truth. So in this instance, the ground truth connectivity matrix would be two sets of diagonal at the middle. That's it. That's all. And you can see that once you started using different technique to measure this connectivity, you get slightly different results. And obviously, you can see that this technique perhaps is one of the better way to do that. So this is a very useful way to directly evaluate any connectivity analysis tool. And more recently, in publishing 2014, is FiberFox, which is an open source tool available as part of MITK. And so this is extending upon the clause, the NFG I just showed in last slide, in a way that allows you to construct a whole brain more realistic tracks. The downside is it doesn't actually model the packing in a realistic way. So I think there's a bit of trade-off there. But because of the mimics, it can create images that are relatively more realistic for the whole brain white matter. It was chosen last year here, here at ISMRM, for the tractography challenge. I think many of you probably already know that. So I'm going to go one more extra step, just looking at how we can use it to go backward looking at data pre-processing, which we need to do, as well as forward looking at how we can use this for group analysis, which I think are useful to mention. So one is some work we did recently, which is by Mark Graham. And so we constructed a full simulator from the prescribing geometry of the model, the segmentations, and how the diffusion should they behave, and going through the full MR simulation with the block equation. And these allow us to capture realistic distortions such as eddy current, motion, and producing images that are very realistic, as well as, most importantly, these sets of ground truth displacement field, which is the standard post-processing tool try to estimate for you. So with this ground truth, we can have a very rigorous framework to evaluate those techniques. And so he's going to present a Monday power pitch session in Diffusion at the cutting edge, the result of using this full framework to evaluate many of the available open source tools for these methods. So you might find that interesting. So one last example is looking at the group analysis. So the reason this is important is because the diffusion tensor imaging is now widely used, a lot of data acquired, and used to look at a variety of from normal development to aging to diseases. And I think one of the challenges diffusion tensor images are tensorial data. They have multi-components and they depend on each other in an interesting way that the standard technique doesn't really capture. So Van Heck, which is did a Ph.D. with Alex Lehman and published a series of papers and really investigated how we can design very sophisticated, serious, thorough pipelines to simulate data set from normal data set to pathology. So this is actually a single graph, but I have to kind of cut in half. So this is in the 2009 paper, refer you to go back to have a look, which I think is a very elegant and impressive attempt trying to tackle this problem. With that, I'm going to just quickly summarize. So hopefully, I demonstrate that numerical phantoms has played and will continue to play in the future an important role in developing advanced diffusion MR techniques. And so I think I put a lot of emphasis on model-based microstructure imaging, where I think the physical phantom or biological phantom are much more difficult to construct and control. And I think in structure connectivity is also useful, but I think some other phantom you'll hear about in the later of the section will perhaps do a bit better than numerical phantoms, and as well as can help us to understand pre-processing and group analysis. And I think its key strengths are its flexibility and controllability. And of course, it means that it can only do so much. It really needs to be used in conjunction with any other form of the phantom you'll hear about later today. And as important point, these are computer programs. As such, they are prone to human errors. So I think they require great care during development and need to be carefully tested in some way. And I think it's a real challenge to develop them as well. So with that, I'd like to thank you for your attention. Thanks my founders, and thanks all the pictures from all the authors who published these works. Thank you very much.